Okay, let's take a look at example 22. This one's going to be real similar to problems 7 and 8 on your homework. We're going to ask you to solve the differential dy dx equals 4x plus 4x divided by the square root of 16 minus x squared. Remember, when it's asking us to solve this differential, all we're really going to do is integrate. So we're going to multiply both sides by dx, so the right hand side's in terms of x. So we're going to integrate this. So the integral of 4x plus 4x over the square root of 16 minus x squared dx. So I'm going to kind of break this up into two parts here. On the left hand side we'll handle the integral of 4x, and on the right hand side we'll handle the integral of 4x over the square root of 16 minus x squared, because that one's going to require u substitution. So the antiderivative of 4x is 2x squared plus c1. And then on the right hand side we're going to have u be 16 minus x squared. It's the most complicated piece there. When we take the derivative with respect to x, we get minus 2x dx. Notice we have to be able to replace the x dx, and the only way to do that is divide both sides by negative 2. So when we do this, we get the integral of 4 over the square root of u times du over negative 2. So we're replacing the 16 minus x squared with u. We're replacing the x dx with du over negative 2. So when we simplify that, we're going to factor out that negative 2. So we're going to end up with negative 4 halves times the integral of 1 over the square root of u du. And then we've done this antiderivative so many times I'm not going to go through all the steps there, but 4 divided by negative 2 is negative 2 there, and then we end up with 2 u to the positive 1/2 plus c. We can factor that 2 out in front, so we get a negative 4 as well, and then we have to substitute in what u was. U was 16 minus x squared, so we end up with negative 4 times 16 minus x squared to the 1/2 power plus c2. Remember, c1 and c2 are both just constants in this problem, so we can write it as c equals c1 plus c2. So our final answer, using the integral on the left hand side and the integral on the right hand side, is just going to be 2x squared minus 4 times the square root of 16 minus x squared plus c. So doing some different parts there and breaking that integral up, still using our u substitution to knock that problem out. Alright, let's talk about even and odd functions. We've talked about that before. We talked about that last semester. Alright, it's about using that line of symmetry. So if a function's even, right, you can substitute in a negative value and then you get the same thing back, right? So a good example of an even function is like a parabola split down the y-axis, right? So everything's the same on the right hand side of the y-axis as it is on the left hand side. If we did an odd function, we were able to substitute in a negative value, and then we get the opposite of the function back. So that's just a slight review on even and odd functions when we did that. So that was the test that we did last semester. You've done it in algebra, we did it in trig. So you should be pretty familiar with what we're talking about when we're talking about an even and odd functions. So there's a couple rules for integration. Theorem 4.16. If our function is an even function and we integrate that from negative a to a of f of x dx, we're going to get 2 times the integral from 0 to a of f of x dx. We're going to work through a couple examples, so hopefully that clears this stuff up. If f is an odd function and we integrate from negative a to a f of x dx, we're going to get 0. Those are going to cancel each other out. So let's take a look here. Let's do an even function. Okay. We're going to take the integral from negative 2. Remember, the limits of integration have to be the opposite of each other, so negative 2 to 2, of 4 minus x squared dx. Alright, let's take a look at the graph first. It's an even function, right? It splits perfectly over the y-axis, so it's 2 even areas. That's why we really just break it into 2 even areas. So we can say that instead of integrating from negative 2 to 2 of 4, we can rewrite this integral, since it's an even function, and say that it's really just 2 times the integral from 0 to 2 of 4 minus x squared dx. Because notice, if we take this, whatever shape that kind of makes, if we cut this parabola in half here from 0 to 2, the same thing happens from negative 2 to 0. So that's why we're saying, hey, it's just 2 times this area when we do this piece. So when we work through this and we take the antiderivative, alright, we're going to evaluate that from 0 to 2. I'm not going to go through all the steps on the antiderivative. That's a pretty basic one. We've done pretty basic integral that you can go through and work through there. So that's really just the concept. We have an even function, being able to split that integral essentially into two parts and multiplying by half of it to get there, or multiplying by 2 to get the other half. Alright, let's do an odd function. So here's a good representation of an odd function. Alright, we have negative pi over 2 to pi over 2 of sine cubed x cosine of x plus sine of x cosine of x dx. Alright, you can check to see if it's odd by substituting in negative 1 for x and seeing if you get the opposite function back. Okay, so I do that on the next page there just so that you can see that it is an odd function. You can obviously see by the graph that it's an odd function as well, right? Remember, an odd function means that I fold it over y-axis and then I can fold it over the x-axis, and if it lays on top of itself after I fold it twice, alright, we can check those sort of things for it to be odd. Okay, so if we substitute in negative 1 for x, we get the opposite function back, so we know that it's an odd function. And the simplicity of this problem is we don't really have to do any work. We know that it's odd, and it's from negative pi over 2 to pi over 2, using our rule up here, our theorem. Alright, theorem 4.16, number 2. If it's an odd function and we go from negative a to a of f of x dx, it ends up being 0. So we can go down here, just a shortcut for doing integrals. Alright, it's negative pi over 2 to pi over 2. We have an odd function. We know that it is 0 here. Alright, the next couple ones, example 25 is really going to help out here with your homework and those sort of things as we go through it. So let's take a look. We have the rate of depreciation of a machine is inversely proportional to the square of t plus 1, where v is the value of the machine in t years after it was purchased. Alright, similar, right? You go to an auto dealer, you drive off the lot, your car automatically depreciates. Machines do the same thing. Alright, so it's the hardest part for you guys is going to be setting this problem up. So the initial value of the machine was $500,000. and its value decreased $100,000 in the first year. We want to estimate its value after 4 years. How much has it decreased? It doesn't decrease $100,000 each year because we have the rate of depreciation, which is dV/dt up here. Okay, so we got to set this up. So our solution is we have to come up with what the value is for dV/dt. Okay, we know based in the verbiage, all right, it's inversely proportional to the square of t plus 1. So inversely proportional automatically tells me I'm doing 1 over something, and then since it's saying t plus 1 squared, I have to take that quantity and square it. So there's also some sort of constant that came into play, so we're going to use k as the constant here. That's the constant we have to solve for using our initial conditions. So if you remember doing that. So this problem's a little bit involved. It's not as tricky as you think, but it does take a little bit of work, and you got to think through the problem. Know that there's some sort of constant affecting this. But the biggest part is understanding inversely proportional means 1 over whatever that something is. Okay, and then we have to take the square of t plus 1, so we're squaring it. So we have to solve for what k is. Okay, we have a couple different initial conditions here. We know that when time was 0, that's when we first bought the machine, it's $500,000, and then we know after 1 year, so when t is 1, the machine has decreased $100,000, so its value is $400,000. So what we need to do though to find capital V, since we know the rate, right, dV/dt is k over t plus 1 quantity squared, we have to find what v of t is, alright, the depreciation as a function of time. Well, we have to integrate that function. So when we integrate, so capital V of t is the integral of k divided by the quantity of t plus 1 squared dt. When we integrate that, you should be able to go through and do that basic integration using U substitution. I'm not going to spend time doing the integration piece. You have to do that. Alright, but I would use U substitution, U is t plus 1, yada yada yada, so on and so forth. When we do this, you end up getting negative k divided by t plus 1 plus c. Alright, then we have to use those two initial conditions we just talked about. So when time was 0, it's $500,000. When time was 1, it had depreciated $100,000, so it's $400,000. So we're going to substitute those initial conditions into our equation here, negative k over t plus 1 plus c, because we have to find what c is using our initial conditions. So when we do this, okay, and we substitute this in, we're going to get negative k plus c equals 500,000. We're going to get negative 1/2 k plus c equals 400,000. Well, this isn't simple. We can't set them equal to each other and solve. We have two equations, two unknowns. Alright, let's take the quick and easy engineering approach. You guys can solve for one variable and do substitution and do algebra. I like to use a matrix approach, plug it in my calculator and get it back real quick. So if you guys remember from trig when we solved some things with matrices, or in the first part of the algebra section here we solved systems of equations with matrices. Okay, we're going to use the leading coefficient. So when we set this matrix up, we're going to have A inverse times B. That's going to give us our solution. So A is a matrix, B is a matrix. Okay, so we use A inverse times B. So we set up the A matrix. Okay, those are the leading coefficients on the variables here. So what's in front of this K is a -1, and this first C, I'm looking at the first equation here, is a +1. So that's why we have -1, 1, and then in the second equation we have -1/2 and 1. So those are the values associated with K and C. Those are our A matrix. Okay, as we substitute those in. So remember that's under your calculator will do the matrix for you. And then we have to do our B matrix. Those are the values here. So 500,000, 400,000. So the first matrix, right, you have to make a 2x2 matrix. You go over, edit it, put it in. And then the second matrix, right, rows, then columns. So this is a 2x1 matrix. When you substitute this in, so you're going to take matrix A inverse times B. So you have to substitute those in. Alright, and then when you hit enter, you're going to get -200,000 for K, and you're going to get 300,000 for C. Now we take those two values for K and C that we just found, and we substitute them into the original V of T equation. Alright, so V of T becomes 200,000 divided by T plus 1 plus 300,000. Okay, so that's the equation that we're looking for, because that's what it asks to estimate the value after 4 years. So the one last thing that you need to do in this step, okay, is up here where it says estimate after 4 years, you have to plug in 4, okay, for T. So you're going to have 200,000 divided by 4 plus 1, which is 5, right, plus 300,000. That'll get you the exact value. So again, I'm not going to go into 100% detail on this because it is similar to a homework problem. You guys need to be able to finish that piece. Alright, let's look at example 26. Okay, example 26, it says the sales in thousands of units of a seasonal product are given by this model. S equals 7450 plus 4375 sine of pi t over 6, where t is time in months. With t equals 1 corresponds to January. We want to find the average sale for the first quarter. Alright, anytime we see average, this one should be a nice easy problem for us. We're just going to find we're going to use the average value theorem, right, which is 1 over b minus a, the integral from a to b of f of t dt. So literally we just have to substitute in. So since we're finding the average sale for the first quarter, that's January, February, March, right? So we're going to go 0 to 3, okay, for our integral. So we're going to have, and those are also our 0 is a, 3 is b. So we're going to just substitute into the average value integral, okay, so it's going to be 1 divided by 3 minus 0 times the integral from 0 to 3 of that function. Okay, then we take the antiderivative of that function. Leave the 1/3 out in front. You can apply that at the end. We're going to evaluate that antiderivative from 0 to 3. Okay, when we do that, we're going to get these values here in the brackets. So we're going to take 1/3 times 223.5 plus 262.5 divided by pi. When we do that, we'll roughly get 102.352 thousand units. Alright, so for more or less the math, the calculus behind it, you guys should be able to do that pretty easy. It's more interpreting the problem, being able to set it up. Example 26 is really going to help you out with problems 15 and problem 16 on your homework. Okay, so that should really make an impact for you guys there. Let's take a look here at example 27. Okay, this is the last example we're going to do in section 4.5. Example 27, we have a manufacturer of fertilizer finds that national sales of fertilizer follow the seasonal pattern here. Alright, because you're not putting it on monthly and things like that. F equals 100,000 times the quantity of 1 plus sine of 2 pi times t minus 60 over 365, where F is measured in pounds. Alright, and T represents the time in days. T equals 1 starting at January. The manufacturer wants to set up a schedule to produce a uniform amount of fertilizer each day. What should this amount be? So we're wanting to find a uniform amount of fertilizer each day. So that problem says, hey, we should produce an average amount of fertilizer each day. So in my mind, this is telling me, all right, I still got to use the average value integral. What's my time frame? Well, we're talking about over a year, okay? And so when we want to do this integration, right? But a year, and we're going to do this up since it's over a year, right? But we want this in days because we're finding the average value per day. So be careful how you set up the integral here. A is 0. B is 365. We're not taking into account leap year or things like that for this problem. So 365 is your B. So it's not like the last problem. We're not going to go 0 to 12 because that would give us per month. We want to go 0 to 365 because we want it per day. So setting up that problem, we're just plugging into the 1 over b minus a times the integral from a to b of f of t dt. When we substitute those values in, okay, we're going to get 1 divided by 365 minus 0, the integral from 0 to 365 of the function. Alright, you have to be able to take the antiderivative of that function. I think you guys all have the skills to be able to do that now. I'm not going to show all the step-by-steps because you're going to have to do a problem like this on your homework. Okay, and I want you to be able to do that. But when we do this and we simplify it out, we evaluate it from 0 to 365, we should come up with 100,000 pounds. So for me, I wanted to be able to explain to you how to set up the problem. I'm not going to do this problem entirely for you because you should be able to do this antiderivative and evaluate it. If you're not getting that, practice it, shoot me an email, those sort of things. But I wanted to help you guys set up those problems. The word problems can somewhat kind of be tricky, but I think once we've done a couple here, it helps you understand what we're looking for. Okay, you just got to pull out the key verbiage on this one. So the key verbiage for us was here, we want to produce a uniform amount of fertilizer each day. Alright, so that tells me I got to produce a certain average each day, and I have to make sure that I'm paying attention to days instead of months in this sort of case, so I had to go 0 to 365. So just kind of pulling the key terms out. Hope you guys are doing well, and we will pick this back up with section 4.6.